Uh, okay, so let's start our ZAC seminar. It's my big pleasure to introduce Anna-Maria Castravet from University of Versailles. And Anna-Maria will speak about blown up toric surfaces with non-polyhedral effective cone.
Thank you very much for the invitation. It's an honor to speak in this seminar. So I want to tell you about some very recent joint work with Antonio Laface, Zhenya Tevelev, and Luca Ugalia. So this is about giving examples of toric surfaces in which if you blow up one single general point, you get a non-polyhedral effective cone of divisors. So before I start with these examples, I want to give you the main application of this. So this has to do with a moduli space of stable rational curves. Oops, sorry, okay. So just quickly to recall, yeah, we're looking at the Lee-Mumford-Knudsen moduli space of stable rational curves with n markings. So this is a compactification, functorial compactification of the configuration space of n distinct ordered points on P1 up to the action of PGL2. So this is a moduli space, a fine moduli space for this moduli problem of taking n distinct points ordered on P1. And you obtain in this way a quasi-projective variety, non-compact. When n is equal to 3, this is just a point. And when starting with 4, if you identify 3 of the points with 0, 1, and infinity, then you obtain essentially n minus 3 copies of P1 without 0, 1, and infinity. So for M04, this is just P1 without these 3 points. And you can compactify this to P1. In general, yeah, the compactification is again functorial. You obtain a fine moduli space for these families, for this functor of families of stable n-pointed rational curves. You have an example here for n equal 5. Yeah, so we are adding to the configuration space 10 boundary divisors. These correspond to loci where you add reducible stable curves with at least 2 components, and then these may intersect and produce more components. So for n equal 5, this is a Del Pezzo surface of degree 5, so a Fano surface. And then if you continue for n equals 6, you can describe this as a blow up of the Segre cubic in P4. This is the unique Segre cubic with 10 nodes. And so in this case, this is not Fano anymore, but it's close. So minus k is a big NF. And then starting with n equals 7, you lose the property of being Fano. In fact, for n at least 8, the anti-canonical is not even pseudo-effective. So that means not only is not effective, but no multiple of it is effective. Yes, so okay. And so we'll be interested in the effective cone of M0n bar. So again, to recall, we're looking in the vector space spanned by numerical classes of divisors. And so inside this vector space, we're looking at effective classes of effective divisors. And we want to take the span of them. This is in general not a closed cone, but we can close it up, and then we want to understand the shape of this cone, as this tells us a lot about the birational geometry of the space. So again, to recall, there is an explicit description of M0 bar as a blow up of a projective space. We start with a Pn minus 3, you blow up n minus 1 points, linearly general position, then you look at the lines spanned by any 2 of them, take the proper transforms, blow them up, and continue in this way with planes spanned by any 3 of the points and so on. And so you blow up everything, all the linear subspaces spanned by these n minus 1 points. This identification is not unique. As you see, the symmetry is broken here. You make a choice of a marking to get such an identification. And then if you do this, you can see that the boundary divisors, so the divisors you added to compactify the space, for one choice of a Kaplanov model, it will be one of the exceptional divisors in the sequence. So in particular, they are contracted by this birational morphism to Pn minus 3, and in particular then this has to be, any such divisor has to be generating an extreme array of the cone. So extreme array just means that if a sum of two things in this cone lies along this array, both those terms have to lie along this array. Okay, and so boundary divisors are extremal. And then for n equal 5, they actually generate the cone. So this is a rational polyhedral cone. These boundary divisors are the -1 curves of this Fano surface, the blow up of P2 at 4 points. And then when you look at n equals 6, you see already that the boundary is not enough to generate the cone. There is some other type of divisor, which was discovered by Kiel and independently by Vermeer. That is not a boundary divisor. These are divisors that will intersect the interior of the space. And then Hust and Schinkel showed that if you throw these in, then these will generate the entire cone. So again, you have a rational polyhedral cone spanned by some geometric divisors. And then continuing this way, the Kiel-Vermeer divisors can be generalized. So we introduced with Zhenya what we call the hypertree divisor. So this is some combinatorial data out of which you can cook out again a divisor with the same properties as the Kiel-Vermeer. So these will be, you can contract them by some, maybe not by rational morphism, but by rational contraction, by rational map. And this will be a divisor that's contracted. And these numbers grow quite fast. Then further, more extremal divisors, when n is at least 7, were constructed by OP, based on the work of Chen and Choshkun for showing that M1 n bar has not a polyhedral effective cone. And then later on also Doran, Jonas Siracusa Jensen, and then Gonzalez, based on their work, found some other divisors. And then just as an amusing fact, I want to also mention that if you blow up just one very general point on M0 n bar, starting with n equals 7, the effective cone is not polyhedral in characteristic 0. This is a work by graduate students Zhuang He and Lei Yang. So this is a bit of a different case. We lose the rigidity of the space here, but I find that this is an interesting result. And so then maybe, so now we have an explanation for why you get all these divisors, extremal divisors. So the application of this result on blow-ups of toric surfaces is that actually the effective cone of M0 bar is not polyhedral starting with n equal 10. And this is true in characteristic 0 and also in characteristic P for all the primes up to 2000. And then you can actually prove that the set of primes has positive density. So we don't quite have it yet for all the primes. Okay, so to explain how this is related to our topic, so I'll define, so we want to reduce to the case of surfaces. And so I'll make a definition, we'll call a rational contraction a rational map between Q factorial normal projective varieties that is a sequence of either small modifications, always assuming Q factorial, or a surjective morphism. Yeah, so a composition of any of these. And so then the statement is that, the observation is that such a map will preserve certain birational properties. So for example, the property of being a monodream space is preserved. This is was introduced by Kiel and Hu. And so then the result that rational contractions preserve this is a combination of results of Kiel and Hu and Okawa. And so monodream space just means that the Mori program works in an ideal fashion. For every divisor essentially becomes NEF on the correct model, small modification. But in particular, it means that every NEF divisor is semi-ample. It also implies that the effective cone is rational polyhedral, has a nice decomposition into finitely many polyhedral cones, which correspond to NEF cones of small modifications of your variety. And then another consequence is that the effective cone is also, if the effective cone of X is a rational polyhedral cone, then the same is true for Y, the target of our rational contraction. This is essentially a consequence of the duality between the effective cone and the cone of movable curves. This is a Buxon de Mailly bone Peternel, which for them is in characteristic 0, but it holds in general. Okay, so then, this came a bit as a surprise, this fact about the effective cone, because it was believed for some time that M0n bar should behave like a toric variety. The similarity between the strata given by the nodes of the rational curves brings a similarity with the strata of a toric variety. And so was expected perhaps that the effective cone is generated by effective cycles of a given codimension are generated by strata, as this is true for toric varieties. So this is not quite true, but it's close. So M0 bar is similar to a blow up of a toric variety. In which sense? So this is a result with Genia that you can squeeze M0 bar between using rational contractions between a blow up of a toric variety, the LOSEV-MANIN moduli space, yeah, so it's the same toric variety, just here it's the same dimension as M0n. Yeah, so this is just a birational morphism. And then here, this is one dimension higher. And we blow up one point on this toric variety, namely the identity point of the open torus. So I'll say a bit more about this moduli space. So M0n is similar to a toric variety, if you want, in the sense that it's similar to the LOSEV-MANIN space, which is a moduli space also of stable rational curves. So from 2 points of view, it's similar. Yeah? So this is also the LOSEV-MANIN space is also an iterated blow up of Pn-3 along n-2 points, and then n-2, all the lines stand by these points, and then planes and so on, just one less point. So this makes the space toric. And then on the other hand, this is also a moduli space of stable rational curves. It's a particular case of a Hassett space where the stability on the curve and together with the markings is given by, instead of taking the canonical, the log canonical, yeah, so the dualizing sheaf of the curve twisted by the points, and you ask that this is ample. Here you throw in some weights for each of the points. And this changes the stability of the curves you allow. So on one hand, in the M0 bar, you allow trees of P1s with then different points on it. And here you will only allow chains of P1s with the heavy points at the ends. Yeah, so in this picture, you don't quite see the difference. There are trees for M0, n equal 5, there are trees in both cases. But what happens is that some of these points are allowed to coincide. And so you're losing some of the boundary divisors. So this is you're contracting some divisors. And then, so so the LOSEV-MANIN space is a toric variety, and it's universal in the following sense, that in fact, if you have any projective Q factorial toric variety, you can always find an n sufficiently large so that you have a rational contraction from the LOSEV-MANIN space into this toric variety. And in fact, moreover, there is a rational contraction between the corresponding blow-ups at the identity point of this toric variety and the LOSEV-MANIN space. So you can decompose this into a sequence of small modifications and surjective morphisms. And so, so this also has then as a consequence that M0 bar is not a Moradin space in characteristic 0 when n is sufficiently large, because using this observation that M0 bar is admits a rational contraction to the blow up of the LOSEV-MANIN space, then we choose a special toric surface, a weighted projective plane with weights A, B, C, which is a special one. Namely, it has a NEF but not semi-ample divisor. It's a result from Goto, Nishida, and Watanabe from '94. And so if you choose this one, then this is not a Moradin space because there is a NEF but not semi-ample divisor. Therefore, M0 bar is also not a Moradin space. And this is now, okay, so this is, there's a restriction here. This is true in characteristic 0, but we cannot use this, this weighted projective plane in characteristic P because, sorry, so this is, can you see this? Okay. I don't know how to move this lower, but okay. So the point is that on this blow up of this toric weighted projective plane, in characteristic P, every Neff divisor is semi-ample, and so this will be actually a Mordin space in characteristic P. Okay, so instead we will look at different kinds of toric surfaces, and so the main theorem is that the main recent theorem is that there exist projective toric surfaces given by so-called good polygons, which I'll define a bit later, such that when you blow up the identity point, you get an effective cone which is not polyhedral in characteristic 0. So this property of being good will guarantee this in characteristic 0. And then in characteristic P, this will also be true for an infinite set of primes of positive density. So there will be primes for which this is polyhedral. And so as a consequence, then you get that also that M0 n bar is not a Mordin space in characteristic P, and you get this actually for n starting with 10, which is the same bound as we had for in characteristic 0. So there I forgot to say that. So there were some other results of Gonzalez and Caru I'm sorry. Okay, okay. So the bound has been lowered to n equal 10. Excuse me. Okay. So there is the result of Antonio Laface, Kijker, and Hausen, who lowered the bound to n equal 10. And so that is for characteristic 0. And now we have the same result also for characteristic P. That this is true for an infinite set of primes of positive density, and it includes all the primes up to 2000. So now I'll give you an example of a good polygon by showing you this picture. And so this is the example that that gives you a rational contraction from M010 to the blow up of the corresponding toric surface. So namely, the rational contraction you obtain by, so you will project, you take a special projection of the normal fan of the LOSEV-MANIN space of dimension 7. So these are the black dots here are the rays of the LOSEV-MANIN space, of the normal fan of the LOSEV-MANIN space after projection, choosing a special projection. And then the normal fan of our toric surface corresponding to the good polygon corresponds to the red dots. Okay, and then what I'm saying here is that once because the red points are a subset of the black points, then you can actually construct this rational contraction here. Okay. So what is a good polygon? So this will correspond to what we call an elliptic pair. So we're looking for some conditions that give you a non-polyhedral effective cone. And so just generally, an elliptic pair, we define it to be a pair of rationals which consists of a rational surface, projective rational surface with log terminal singularities, and an arithmetic genus 1 curve with self-intersection 0, and which is disjoint from the singularities of X. So typically this will be a smooth elliptic curve. And then we consider the orthogonal complement in the divisor class group of X to this curve C, and we consider the restriction map to C. So we restrict the divisor to C, and note that here C is contained in C perp. And then we define the order of the elliptic pair to be the order of the restriction of C in peak 0 of C. And so this can be infinite, but in characteristic P, this is always finite. Another way to characterize this order is to say that if this is finite, this is the smallest integer such that this multiple of C has at least 2 linear independent sections. And so there are two situations. Either the order is finite, in which case the order gives you, there are exactly two linear independent sections here, and you get a morphism to P1, which the generic fiber here is an elliptic curve. C is a multiple fiber. The other possibility is that the order is infinite, in which case, yes, there are any multiple of C has exactly one section. And so it's, we claim this cannot happen if the effective cone is polyhedral and the Picard number is at least 3. So this is an argument that goes back to Nikulin. So the first part is immediate, yes. So for the second part, if you have a surface with a Picard number at least 3 and the polyhedral effective cone, then you can actually prove that the effective cone must be generated by negative curves, and every reducible curve with square 0 has to be contained in the interior of a facet of this polyhedral cone. So in particular, multiple will have to move. You cannot have the curve C to be rigid. So this last observation just comes from the light cone of curves with self-intersection, positive self-intersection will have to be contained in this cone, but this is if the Picard number is at least 3, this is a round cone. And so you use that to argue that that such a class C has to be contained in the interior of a facet, of a class with C square equals 0. Okay, so this is our criterion for showing that an effective cone of a surface is not polyhedral. And so we will have to apply this for some special types of elliptic pairs. But before we discuss that, so I want to also discuss what happens. Sorry, just going back. Yeah, so we have non-polyhedrality when the order of the elliptic pair is infinite. In this case, I didn't say anything about polyhedrality. So if we will be interested in this case too, because we're interested in the characteristic P case. So in general, so here we will we'll be able to give a criterion for polyhedrality, but we have to get some extra assumptions. So in general, so we'll have to consider what we call a minimal elliptic pair. So this is an elliptic pair such that there are no irreducible curves such that they intersect K negatively and C in 0. And so every elliptic pair has a model which is a minimal. So there is a morphism, which is an isomorphism in the neighborhood of C from X to Y, such that Cy now considered on Y is an elliptic pair and is minimal. The order doesn't change because it's an isomorphism in the neighborhood of C. And so to see why this is true, there are just a few observations that are also will be useful. So by adjunction here, you have K plus C restrict to C trivially. So K intersects C is 0. The fact that the pair is minimal can be seen, it's not hard to see that this is equivalent to K plus C being NEF. And then, so we're using here that C is C squared is 0. And then by the Hodge index theorem, we can also prove that the fact that C squared is 0, K times C is 0, and if K plus C is NEF, then K plus C will have to be a multiple of C, some rational multiple of C. And then you run K plus C MMP, you contract the curves that intersect K negatively and C in 0. And okay, so this will lead to this Y. And so further, we can consider a reduced restriction map. So we define also CL0 of X. Yeah, so this inside C perp, we mod out by the subgroup generated by K. And so then we consider the induced map coming from the restriction map to C. And then, so what we need in order to be able to characterize polyhedrality when the order is finite is two conditions. One is that the elliptic pair is minimal, and the other one that that the surface has Duval singularities. So assume we have such an elliptic pair with dual singularities, and we consider its minimal resolution. Then we have equivalent statements, yeah, that the pair CY is minimal if and only if its resolution is minimal, and that's equivalent to the Picard number being equal to 10. And in this case, you can prove that CL0 on Z is the lattice E8. And then here is the criterion of polyhedrality, namely, so if you have a minimal elliptic pair with dual singularities, Picard number at least 3, and the order of the pair finite, then the effective cone of Y is polyhedral if and only if the effective cone of Z is polyhedral. And then there is an equivalent condition that this reduced restriction map here. Okay, so this is a reduced restriction map of Z. Sorry, I didn't write this here. Then this contains 8 linearly independent roots, -2 classes in E8, identified with CL0 of Z. Okay, so I'm saying that we need, in order to get an if and only if condition for the effective cone being polyhedral, we need this minimality and, okay, an extra condition on the singularities. Okay, so what is the upshot? So if you have, so we'll have, for any elliptic pair, we can consider its minimal model. And so there are 2 cases. Yes, if the order of the pair is infinite, then the effective cone of X and that of Y is not polyhedral because the order is infinite on both. If, again, the Picard number is at least 3. And in this case, it does happen that that Y is actually has dual singularities, as the fact that we are assuming, yes, that C restricted to C is not torsion. And this actually implies, by our observation, that K plus C has to be a rational multiple of C and restricts trivially to C. This actually implies that minus K is actually equivalent to C. Okay, which is an equivalent condition to Y being having dual singularities. And then the other case is that if the order is finite and in addition Y has dual singularities, then we have this polyhedrality criterion where you cannot say anything perhaps about X, but you can say something about Y. In terms of these roots, you may have to move to the singularization, and so on. So I'll do that on an example. Okay. So then the problem becomes the following. So assume that you have a C and an X that are defined over Q with order, in infinite order. Then assuming that we can extend to a morphism over spec Z, and yeah, so outside perhaps some primes of bad reduction, then if on the generic fiber Y is dual, then you can also see that on the reduction mode P is also dual. And then yes, so for these primes, then the order is finite, and we want to study here the polyhedrality, if the polyhedrality criterion applies for Y, so for the YPs here. Okay, so now in our case, yeah, so the elliptic pair will be coming from a toric surface. So I would consider a lattice polygon, and so this corresponds to a toric surface, a lattice polygon in the plane. We'll have a toric surface with an ample divisor L delta on it. And so our X for our elliptic pair will be the blow up of this toric surface at the identity point. And then I'm going to fix an integer M. And so here's what we mean by a good polygon. We want to look so on the blow up of the toric surface at the identity point. We want to look at the linear system given by L delta minus ME. And we want to construct here our elliptic curve with self-intersection 0. So the condition is that there is an irreducible curve in this linear system that gives an elliptic there with order, infinite order. So translating this, we want that C is contained in the smooth locus of X. So that's equivalent to the Newton polygon of C coinciding with delta. And then the fact that the self-intersection is 0 is equivalent to the volume of this polygon. So the square of this L delta is equal to M square. And then you can further see that having arithmetic genus for this curve is equivalent to the number of lattice points on the boundary, on the edges of this polygon being summing up to M. And then we also want that the order of this, so when we restrict C to C on X, this is a not torsion line bundle in peak 0 of C when considered over Q. Okay, and so so then the theorem is that, yes, and this is now immediate out of what we saw so far, is that if you have a good polygon, then in characteristic 0, the effective cone of X is not polyhedral in characteristic 0. This was this observation that if the order of the elliptic pair is infinite, the Picard number is at least 3, then the effective cone is not polyhedral. So now I want to run an example to see what we do. Yes, with our problem of finding the primes for which this is still non-polyhedral. So, for example, in this example here, I claim that that the area of this polygon here is 49 over 2. So the volume, this corresponds to the volume being, so the corresponding polarization having square 49. There are 7 boundary points, lattice points. And then, so now we claim that in this linear system corresponding to this ample divisor minus 7 times E, so in this linear system corresponding to this ample divisor, there is a unique curve which has multiplicity 7 at the identity point. It has this equation here. And so this is a Bachmann calculation that does this. And this curve, then you can see that the red terms correspond to the vertices of this polygon. So the Newton polygon is our polygon delta. And okay, and then you can actually use the database for elliptic curves and find that the minimal Weierstrass equation has this form. So it's actually a smooth elliptic curve. And the linear system, this L delta minus 7E is actually has a single member, this curve. The Mordell-Weil group, so this again comes from the database. The Mordell-Weil group is Z times Z with generators given by these 2 points. Here you identify peak 0 C with C. And then a computation here is that, so this requires some effort. The restriction of C to itself, this is on our surface X, when you express it as a point on this curve, here it's exactly this point here, -1, -2. And so you can see that it's actually not trivial. It's not the identity of this, it's not the point at infinity of this elliptic curve. And so it's, this is, and the Mordell-Weil group is Z times Z, so this is not torsion. Yes, and so, so this, we already know that this is a good polygon because the restriction of C has infinite order. Okay, so further now, yes, I want to go in the direction of yes, the problem of finding what happens when you reduce modulo P. And so, so this comes with we have to understand how to find the minimal model of this elliptic pair. And so, if you look at the minimal resolution of this toric surface corresponding to our good polygon, I've always will work from now on. I always work on this example. Yeah, so you can find its resolution. Yeah, I'm giving here the normal, the fans, the rays of the normal fan. Yeah, so in bold we have the rays of the original normal fan of delta. And so what you see here is that there are in fact 2 one-parameter subgroups that have widths equal to 7 with respect to our polarization. So they are here. So they correspond to these rays here, and then U equal V. So what this means is that this resolution, the smooth toric surface, admits a map to P1 times P1, and these 2 one-parameter subgroups are fibers. This P1 times P1, and we take their proper transforms on tilde P delta. And then if you do this also after blowing up the identity point, the fact that these one-parameter subgroups have widths exactly 7 makes them intersect this. So the intersection with this polarization is 7 on the toric surface. And then if you, on the blow up at the identity point and the intersection, this proves that the intersection with our curve C, which has multiplicity 7 at the identity point, is actually 0. So you have 2 minus 1 curves that intersect C in 0. And these will be part of the curves that we need to contract to get to the minimal elliptic pair corresponding to this X, this one. Okay, and so this is the setup. We're looking at this elliptic pair given by our good polygon, blow up the identity point, and then we look at the Zariski decomposition of K plus C. So it turns out these are the curves that we need to contract. So it contains here the 2 one-parameter subgroups. So one with multiplicity 2, and then there is one more curve here which is not a one-parameter subgroup. It doesn't come from a one-parameter subgroup, but it has a multiplicity 3 at the identity point. And then yeah, so contracting these curves will get us to the minimal elliptic pair. So in general, we have a commutative diagram here that, yeah, so from X you go to the resolution. You can also find the minimal model of this elliptic pair given by the resolution will be a elliptic pair with a smooth rational surface, which is actually the minimal resolution of Y, our minimal model of our elliptic pair. Yeah, so on X we contract 3 curves, these curves C1, C2, C3, and we get to we get to the minimal elliptic pair of X. Its minimal resolution, we call it Z, and it's also the minimal elliptic pair corresponding to the resolution. And so in this, in our situation here, in our example, we started with a heptagon, and so and we blow up the identity point. So the Picard number of P delta is 5. The Picard number of X is 6. We contract 3 curves. This is Picard Y has Picard number 3. And now we are trying to analyze the polyhedrality of the effective cone of Y in characteristic P. And okay, so now this is, so we'll have to look at this criterion for polyhedrality, looking at finding these 8 linearly dependent roots in E8 that have image 0 by this reduced restriction map. And so here is a computation again that again requires some effort to show that the sublattice spanned by the class of -2 curves about the singularities of this Y is is this one. You have two chains of -2 curves, one with 6 curves and one a single one. And then, yeah, so the CL0 of y, what I call CL0 of y, is just obtained by you quotient out CL0 of z by this sublattice. So this is now, this quotient is actually z. And so we're looking at this restriction map from CL0 of y into P0 of c modulo the subgroup generated by this point Q. Okay. Okay, this was the restriction of K. And so then our criterion, the consequence of our criterion is that the effective cone of Y is not polyhedral in characteristic P, if and only if we can find so all the roots that of E8 which are not in T do not get sent to 0 by this reduced restriction map. Yeah, so here we already know that all the elements of T will restrict trivially. It's just that, yeah, so this is a rank 7 lattice. So if we cannot add one more, yeah, otherwise we get the polyhedral cone. So this is the condition that, yeah, we want to understand all the roots which are in E8, and then we want to take their image, take their restriction to C, and then check if that belongs to the subgroup generated by this point here. Okay, and so so this is now becomes very explicit. So in this quotient here, we can write down in terms of if you choose a generator for CL0 of Y, you can actually prove that the roots of E8 are going to be multiples of this generator when I take their image in Y. And so the condition then is, so then, okay, you need to compute what is the restriction of such a generator when you restrict to C. And you can prove, this is a computation to prove that this is given by this point, yes. And then, yeah, so the condition is we want here that the effective cone of Y is not polyhedral in characteristic P if and only if all the multiples from 1 through 4 of this point P do not belong to subgroup generated by Q. And here, I mean, I want the reduction of these points modulo the prime P. So let me, so this, I'm sorry, this is the correct way to write this. Yeah, so we want to look at this condition. We want none of these multiples to be in the subgroup generated by Q after reducing modulo P. And we want to prove that this has a positive density. And then this is now, so the one, it suffices to check, for example, the following, that if you fix a prime Q, then you look at the primes such that this new prime Q divides the index of the subgroup generated by the reduction of Q inside the FP points of C, and Q does not divide the index of the least common multiple of these multiples here times P, the reduction of P. And we want this to have a positive density. And now this is a consequence of two theorems, the Chebotarev density theorem and Lang-Trotter's theorem. So the Lang-Trotter gives you exactly a condition that this happens, that Q divides the index of a subgroup generated by one point and doesn't divide the index of a subgroup generated by another point. And so it can be formulated like this, yeah. So if you have 2 points of both of infinite order which generate a free abelian subgroup, okay, I think this is a typo. This should be a C, sorry, C of Q. Okay, then you have a set of primes of positive density such that Q divides the index of the subgroup by the reduction of one of the points, but not the index of the subgroup by the other. And so, okay, then for our example of a good polygon, for example, these are the primes under 2000 for which this is true. So I should say here that, yeah, that a lot of the calculations are, this is a magma calculation. And then there are some other facts that, for example, yeah, so you can classify the good polygons with volume up to 49. There are 100, they correspond to 135 toric surfaces. And then you can also just say, look at the pentagons, and you can construct an infinite sequence of pentagons such that, yes, for each of these pentagons, they are good pentagons, so they, in characteristic 0, they give you examples with non-polyhedral effective cone, but for any prime, the effective cone will be actually polyhedral. And then there are many other examples here, but you can also construct infinite sequences of good heptagons. And for these, for all but finitely many, you have again the set of primes which give you non-polyhedral effective cones has positive density. Okay, so I think this is what I wanted to say. I finished early. I'm sorry.
It's okay. Thank you, Anna Maria. Let's thank Anna Maria. Okay, and in Zoom like this. Okay, thank you very much. It was very explicit talk. Everything was crystal clear. And thank you. So any questions? Mm-hmm. Okay, maybe I ask like a general question. So, so your result basically main application is a compactification of M0N, yeah?
Yes.
Particular one, and maybe for example,
and some other ones. I mean,
some other ones. Other compactifications which can be considered like some maybe which.
So any, so in particular, the blow up of the LOSEV-MANIN space at the identity point is a Hassett space. Okay. So in particular, this one also will, and any further blow up. So there is a space of Hassett moduli spaces in between M0 bar and the LOSEV-MANIN space. So, or the blow up of it at the identity point, and any of those will have the also non-polyhedral effective cone because they project, they have birational morphism to that.
Okay, thank you. Any other questions to Anna Maria? Okay, if no more questions, let's thank Anna Maria again. Okay, let me fix it. Okay, I'll stop recording and